In 1835, French scientist Gaspard Gustave de Coriolis invented and published the theory that any moving body on or above the Earth's surface, such as an ocean or air current, will tend to drift sideways from its course because of the Earth rotation. Hello, I am Kuntal Gonguli, and you are in Knowledgeopedia brainstorming session about how a Coriolis mass flow meter actually works.
A body in moving surface experiences a sideways deflection. The stream of water is also had same deflection when not even touching Earth's surface, means it's not about centrifugal force. It's called Coriolis force. The force pushing the objects sideways is called the Coriolis effect. As you can see, perception of straight-ahead movement in a rotating platform is not at all what are expected. It appears that something is pushing the moving body sideways at angular direction from its straight destination expected. This is the effect of the Coriolis force.
Let's have a look inside a single-tube Coriolis flow meter. An excitation coil creates a constant oscillation of tube. When there is no flow inside tube, the oscillation also uniform. Pickup coil at tube inlet A and outlet B registers the same signal. When there is a flow, additional tube deflection observes due to Coriolis effect and creates a time and space differences of both pickup coil and B signal with respect to each other. This is known as phase shift. It is directly proportional to mass flow.
Pickup coil located at both inlet and outlet are very accurate and sensitive to register any minimum deflection observed in the tube body. More flow creates more oscillation, and thus higher phase shift represents higher mass flow rate. Signals evaluated are electronically processed further to eliminate the noise signals and represents the mass flow rate with respect to time and present totalized value.
Inbuilt PT1000 registers the medium temperature.
Sensors also registers oscillation frequency of the metal tube filled with processed liquid or gas medium. In such a way, it also detects if the tube is completely filled, empty, or partially filled with medium, which creates instability of targeted movement and represents an homogeneous state of filled medium. As a result, tube filled with water oscillates lesser than if the tube filled with heavy furnace or with higher density. Means oscillation frequency is directly proportional with fluid density. Same formula and principle apply with dual tube design widely used in present industries. This design offers more stability and accuracy, but with a little higher pressure loss compared to single tube design. Inside a dual tube sensor, two metal tube oscillates across each other, supporting by a torsion rod or beam. The same like a tuning fork. Differentiating the single tube design pickup sensors of inlet and outlet here placed at perfectly fixed torsion plate chamber exactly at metal in between the two parallel tube. These sensors detect phase differences between two tubes and evaluates oscillation. Based on range of detected oscillation frequency and with the help of some settings, medium type and status like empty, filled, partial condition could easily be identified. With the help of inbuilt temperature measurement, it is also possible to identify concentration in fractions based on table incorporated with some higher version of instruments. Thank you for watching.